Okay, so these are the multiple choice questions. So this first one, we're asked what the volume of gas is in Y. So in X, there is M, lots of gas. In Y, it's half the volume, so the pressure has to be the same because they're connected, so it's half the volume, so it must be half the mass, but it's also at 4 times the absolute temperature. And to have the same pressure at 4 times the absolute temperature, there must be an additional 4 times as much gas here at 4 times lower temperature. This has to be have 4 times the temperature to apply the same pressure. So this one is 1/8. So Y must be at 1/8 of the mass, because Y is 4 times the temperature and half the volume. So this one's about the specific heat capacity. So we have 200 grams of water, which is 0.2 kilograms, at 23 degrees and goes up to 79 degrees. So that's a 56 degree or 56 Kelvin temperature difference. So Q equals MC delta T. That will allow us to work out how much energy that was. So the total energy required to do that is the M, which is 0.2, the C, which is 4,200 because it's water, and then times by 56, so that's temperature difference. So we can multiply those together. So 0.2 times 4,200 times 56 gives us 47,040 joules, but then that happens in a minute. So the average power, if I divide that by 60, so Q over T, that divided by 60 will give me 784 watts, which is A. This one, we're asked for the root mean square speed of the particles. So we've got 3 particles. So the root of the mean of the square of the speed. So we square the speeds, we get 16, 36, and 4. Find the mean of the speeds. So 16 plus 36 plus 4 is 56. And then we find the square root of 56. So we get 2 root 14, which is 7.4833. And that's commonly the common wrong answer. You see it's B. What you've done there is you found the sum of the square of the speeds. You haven't found the mean of the square of the speeds. So you need to do 56 divided by 3. And that will then give you the mean of the squares, which is 18.6 recurring. Then you square root that, and you get 4.32 meters per second. If you look at that, then that should be similar to these values. So a 6, 4, and a 2, 4.32. That seems entirely sensible as an average value for those speeds. So this one is about Brownian motion, demonstrated using smoke particles in air. Experiment makes it possible to see the motion of air molecules. Not really. The motion is caused by the collisions of the smoke particles with each other. Not really. The motion is caused by collisions between air molecules and smoke particles. Yes. Motion occurs because air is a mixture of gases and molecules are different. That would happen even if it wasn't a mixture of gases. So the best answer of these is the third one, that the motion is caused by collisions between the air molecules and the smoke particles. Okay, this next one, the gradient of a potential distance graph. Well, the gradient is the rate of change of V with respect to D. V is Gm over R, in this case over D. So V, generally speaking, would be Gm over R. Differentiate that with respect to the distance, you're going to get Gm over R squared, which has the units of the gravitational field strength. And you should know that the gradient of a potential distance graph is also a gravitational field strength. So D. Okay, the next one. Distance between the Sun and the Earth is 1.5 times 10 to the 11. What's gravitational force? You could do this with circular motion. You could do F equals mv squared over R. Working out like that. But I think it's going to be easier to do it Gmm over R squared. You should get the same values. So we get 6.67 times 10 to the negative 11. mass of the sun is 2.0 times 10 to the 30 kilograms. Earth's mass is 6 times 10 to the 24. All divided by the separation of the Earth and the Sun, which we're given, which is 1.5 times 10 to the 11, but don't forget it needs to be squared. So we calculate those. So 6.67 times 10 to the negative 11 times 2 times 10 to the 30 times 6 times 10 to the 24 divided by 1.5 times 10 to the 11. But remember it's squared, so we'll do that twice. We get 3.56 times 10 to the 22 newtons. And that's not one that I have a feeling for. That's not one I calculate, but then so I might go back and check that. So that's A. Next one. Small object of mass m, charge q. Object remains stationary in an evacuated space between two horizontal plates. Two horizontal plates, so this is a uniform field. And we can, given by the potential difference divided by d. Uniform all the way along. Plates separated by distance d. Potential difference between the plates is v. And we're asked to express v using algebra. So we can work that out by the field strength. So v is given by, or the electric field strength rather, is given by v over d. So the electric field strength is the size of the force on this charge. So v equals ed. And the force on the charge is given to us, and we can work that out. And we're also given that it's stationary, so the charge due to the electric field must be equal to the weight. So we can then state that E equals mg over q. So then V equals mgd over q, which is mgd over q, which is B. Okay, this one, we've got two plates. We've got two parallel plates. And if you were to draw the field lines, you would be drawing parallel lines equally spaced. And from GCC, you should know that if you've got equally spaced parallel lines, then the field strength is uniform. Uniform means that it's the same strength at at all the different points. So this one is just A because it's the only one that has the same field strength all the way along. So they're trying to catch you out there. The next one, planet N has gravitational potential negative V at its surface. Planet N has that. Planet M has double the density and double the radius. Both planets are spherical, have uniform density. What's the gravitational potential? So we're comparing the potentials based on this. So double the density, mass is density times volume. So double the density, and planet M has twice the mass. Double the radius. Well, if you double the radius, then actually because the volume goes with 4/3 pi r cubed, then actually if you double the radius, then it's got 2 cubed times the mass. So we've now got 8 times the mass. So we're up to 16 times the mass. But the surface is now twice as far away. And the gravitational field strength, G, is inversely proportional to the square of the radius. Therefore, we're twice as far away. So now we divide by 4. So we should have a value 4 times less. But this is talking about the gravitational field strength, not the potential. So we need to actually be thinking about the potential rather than gravitational field strength. So I've solved that as if I'm solving gravitational field strength because I'm rushing and I need to read the question. So some of the work I've done is valid, but what I need to do is then sort of step back and think, right, hang on. So V, although the masses are valid, so I've got 16 times the mass, that's true. So it'll be 16 times the potential. Rather than varying with 1 over r squared, V varies with 1 over r. So rather than 4 times less, I need to be half as much. So it should be 8 times the potential value, so that will be B. Okay, so we've got a few tricky ones, and then we get a surprisingly easy one. Positive charge in a field where the potential is plus 500 volts. Well, then the energy is just QE. So it's just 2 times 10 to the negative 4 times 500. And that's 1,000 times 10 to the negative 4, which is 0.1, which is A. Next one, 2-point charges P and Q are 100 millimeters apart. So that's 100 millimeters is 0.1 of a meter. X is on a point between the two where the potential is 0. And we have the two charges there. What's the difference? Sorry, what's the distance between P to X? Okay, so electric potential is inversely proportional to the distance. And effectively, if you were to draw this out, you'd actually have this is positive, and then it will go to negative down here somewhere, where actually this distance should be much closer to this. I'm not drawing that very well. I'm doing it with pen as well. So it should be much closer to that one than this one. It's going to be, this has 3 times the effect, this has 2 times the effect, so it's 1.5 times the effect of the other. So it should be 1.5 times closer to this one than this one. So 100 millimeters split into 1.5s. So we can do it in 6s or we can do it in 3s. So look at it in terms of 3. So you've got 3 and 2. So 3 plus 2 gets me into a proportion of 5. So it's how do we split that 5? So each section is 100 millimeters, ends up being 20 millimeters, and it needs to be 3 because it's 3 and this is 2 in terms of the magnitude. So this has got to be 3 times 20 millimeters, and this has got to be 2 times 20 millimeters. So you end up with B being 40 millimeters. You can work it out. So you can work it out using the fact that V is 1 over 4 pi epsilon naught multiplied by Q over that distance R is equal to, and that would be Q at point Q. RQ is equal to 1 over 4 pi epsilon naught multiplied by Q due to P over the distance to P. And you can solve it, they will cancel out. You can solve it as a simultaneous equation, but it is often easier to work these out using ratios.